Hello, this is Hans Johansson and welcome to 1298. We're presently in a windowless, airless room. I would say this is the material phase of the Newtonian paradigm. This is anti-knowledge. This is trying to eradicate everything that is knowing. Doesn't get any more senseless. There's no abstract, there's no intellectualization here. It is just the trenches, as we used to say when I studied English. Welcome to the trenches. This is where knowledge gets destroyed. But on the positive side, we have Roberto, Mangabeira, Unger and Smolin. They herald hope in a dark world, and not hope as hope itself or faith or trying to convince oneself. I think that's most usually the case, saying that it should be better and hoping for it. No, it shows that the thing with the problem is the Newtonian physics, not the other way around. That's where everything started. Unassumed expectations. And the fallacies that erodes knowledge from within itself. I should just see if I can find a better chair here. This one is... The failure of the Newtonian paradigm to satisfy the principles for a cosmological theory. It should be immediately clear that any theory formulated within the Newtonian paradigm fails to satisfy several of the principles stated above. Let us begin with a PSR. It demands that there be a rational reason for every property of the universe. And this certainly includes the choice of laws and initial conditions. Could there then be, within the Newtonian paradigm, a rational reason for such a choice? There have been several proposals for how the sufficient reason might be supplied. The most important of these, which was very influential during the 20th century, is that there is but a single mathematically consistent theory that unifies the fundamental particles and interactions. Stated this way, it fails right away, because you can ask, what is the sufficient reason for a universe to have the four forces we observe? Let's start with gravity. We know that there are consistent mathematical descriptions of worlds without gravity. These are given by conventional, classical, and quantum field theories. Or let us ask, why the quantum? We know there are consistent theories of possible worlds. With or without quantum mechanics. But perhaps what is meant is that there is a unique, mathematically consistent quantum theory that includes gravity and some mix of gauge fields and fermions. This was initially the hope of string theory, and on present evidence it is simply not the case. Nor do any other approaches to quantum gravity give reason to hope that there is only one consistent mathematical description of a world where gravity and quantum physics are united. Loop, quantum, gravity seems equally consistent, coupled to any set of gauge fields, fermions, and scalars. One might posit that the list of consistent theories is reduced down to a unique case by the anthropic principle. But there is no reason to suppose this is the case. Indeed, many of the parameters of the standard model of particle physics can be varied within large ranges without affecting the possibility that life exists. These include the masses and couplings of the two more massive generations of fermions. The bottom line is that mathematical consistency is simply too weak a requirement to supply sufficient reason for the choices of the known laws of nature. This remains the case even when supplemented by the anthropic principle. Almost the opposite proposal has been made as well. There are many consistent mathematical descriptions of possible universes, and they all exist. We happen to live in one of them, picked out, but far from uniquely, by the anthropic principle. This fails the criteria of good science, because the main hypothesis, a vast or infinite set of other universes, disconnected causally from our own, is in principle not subject to any kind of check or confirmation. This also fails the principle of sufficient reason, because when every property or choice is manifested in some universe, there is nothing to explain. There is then no possibility of sufficient reason for the choice of theory within the Newtonian paradigm. The fact is that there are a vast or infinite number of possible configuration spaces. And on most of them, an infinite set of possible dynamics. Restricting to quantum theories or use the anthropic principle does not change that. We reach the same conclusion when we ask whether there could be a sufficient reason for the choice of initial conditions. It suffices to restrict attention to the initial conditions of a single theory. General relativity, coupled to the matter fields which are observed. If we neglect quantum effects to begin with, this is a completely well-defined theory, and it has infinite dimensional space of solutions. Each of them is a possible universe, but at most one of them describes our universe. Even if we restrict by the anthropic principle, that leaves an infinite number of solutions that are roughly like our universe. So, there is a choice, and within the theory there can be no rational reason for one solution to be picked over another. If we ignore this and believe in the application of this theory to the whole universe, we end up asking an apparently silly question. Why does the theory of the whole universe allow an infinite number of solutions when a single one would suffice? Because there is only a single case for the theory to apply to. This question just restates the failure of any theory within the Newtonian paradigm to satisfy the PSR when applied to the whole universe. The failure of the Newtonian paradigm for elementary events. Remarkably, the Newtonian paradigm doesn't only fail when applied to the universe as a whole. There is an argument that it must also fail when applied to the most elementary events. This argument begins with a discussion of the limits of reductionism. Reductionism and its limits. Reductionism is the good advice that if you want to understand a composite system, which means a system composed of parts, you will do well by explaining the properties of the composite system in terms of the properties of the parts. The same holds for compound processes, whose properties can often be usefully explained in terms of the interactions of the properties of the sub-processes that make it up. There are many cases where the properties of the composites are not of the same kind as those of its component parts or processes. This occurs when the properties of the composite would not make sense when applied to the parts. In these cases, we must say that the property of the composite is emergent. By which we mean that it must be invented and added to the list of properties. For example, a liter of gasoline can have a mass, a momentum, a temperature, and a density. Its component molecules have mass and momentum, but it makes no sense to talk about the temperature or density of a molecule. Ignoring its internal degrees of freedom. So we say that temperature and density are emergent properties of the gas. This common circumstance does not represent a limit of the method of reductionism. Instead, it represents its intensification. For emergent properties, in the sense I've defined them here, can often be elucidated in terms of the properties of the parts. This is the case for both temperature and density. The temperature of a gas, for example, was discovered to be the average kinetic energy of its constituent molecules. But there is a limit to reductionism. The method of reductionism can be iterated as the parts are broken up into smaller parts. But it fails the moment we get to a level of constituents that are deemed to be elementary, meaning they have no parts. But they still have properties, and reductionism is moot as to how we are to explain them. Let us suppose that the quarks and electrons of the Standard Model are truly elementary. That is, they have no constituents, so their description in terms of local quantum fields is exact down to all distant scales. Then their masses and chain charges would be in need of explanation, and this by assumption cannot come out of further reduction. How are we to proceed? Relationalism offers a strategy that can take over at the point that reductionism fails. The properties of elementary particles can be understood as arising from the dynamical network of interactions with other particles and fields. A property of a particle or event that is defined or explained only by reference to the network of relations it is embedded in can be called a relational property. Its opposite, a property that is defined without such reference to other events or particles, is called intrinsic. The ambition of a purist relational approach would be satisfied if all properties of elementary particles and events are relational. An early attempt to realize such a relational explanation of the properties of the elementary particles was the bootstrap approach of Chu and collaborators, developed in the 1960s. They situated the observed hadrons within the complex network of interactions in which the properties of composite and constituents were mixed. That is, a proton was composed of a neutron and a pion, but the neutron was also a composite of a proton and a pion, while the pion was a composite of the proton with the anti-neutron. These relations gave a coupled nonlinear set of equations for the amplitudes of these processes of compositedness. They conjectured that mathematical consistency plus a few basic properties would constrain these amplitudes sufficiently to give a unique set of properties to the elementary particles. The bootstrap program failed at the time to produce results that supported this conjecture, but it has recently been revived by combining it with another seemingly failed program, twistor theory. And shown to work in the case of quantum gauge theories with maximal supersymmetry. But the original Bootstrap program was superseded in the early 1970s by the standard model of particle physics, which is a conventional quantum field theory in which the protons, neutrons and pions emerge as composites of elementary quarks and gluons. So this was a further victory of reductionism. However, the standard model of particle physics is only partly reductionist, for it is partly relational. The quark and lepton masses all come from their coupling to the Higgs field, and through those couplings depend on the phase of the vacuum. In a symmetric phase, the masses all vanish. In a spontaneously broken phase, they are all proportional to the resulting vacuum expectation value of the Higgs field. In more highly unified models, the Higgs potential can be quite a bit more complex, with many local minima, each of which is characterized by a pattern of symmetry breaking, which in turn defines a different phase of the quantum field theory. In each of these, the properties of the elementary fermions will be different. It seems like the larger the symmetry and the greater the unification, the more potentially complex the Higgs potentials are, and hence the larger the possibility that the elementary particles have available to them a potentially large number of arrays of properties to choose from. Of course, this does not explain everything. the quark and the lepton masses are all different because each is proportional also to a coupling constant by which they couple to the Higgs field. And these are among the unexplained parameters of the model. These are not so far explained relationally. We will come back to the question of whether the pure relationalist ambition can be satisfied or whether some properties of elementary events or particles all turn out to be intrinsic. We need to first consider a consequence of the principle of the identity of the indiscernible for the description of elementary events. The uniqueness of fundamental events. For a naturalist, the universe being the totality of all that exists must be unique. For a relationalist, this unique universe must contain all of its causes. But a little known consequence of Leibniz's principle of the identity of indiscernible is that every elementary event must be unique in the sense of being distinguishable from every other event in the history of the universe by its location in the network of relations. It is most straightforward to make this argument within an ontology in which the history of the universe consists of discrete events whose relational properties are fundamentally causal relations. But the argument can be made in other ontologies as well. These events may, as we have just discussed, also have intrinsic properties. But they have no intrinsic labels. If we want to refer to a particular event, we cannot just give it a name such as event A. We must give it a unique description in terms of its relation to other events. Which uniquely distinguishes it from all the others. And in that description, you cannot just say event A is the one whose immediate causal past is events B and C. For B and C must be specified relationally as well. So the description must be based on the past causal set, going far enough into the past that event A's causal past is distinct from the causal past of any other. So the point is that elementary events are not simple to name, because a complete specification in terms of relational properties must contain enough information to single each out from the vast number of other events in the history of the universe. Given this, let's consider what goes into spelling out the most elementary causal relations. That is, events B and C are the direct causal progenitors of event A. Developed in enough detail to relationally describe or address the free events. This is a highly complex statement that carries a vast amount of information. So elementary events are not simple, and neither are elementary causal relations. It follows that at the fundamental level, nature cannot be governed precisely by laws that are both general and simple. A complete law of nature would have to explain why event A occurred, which means why the events B and C gave rise to a new event. To give a definite answer to this question would be to pick out which pairs or small sets of events give rise together to new events. As there are vastly more pairs or subset that do not have common immediate future events. The question is what makes B and C different from the vast numbers of pairs that do not give rise to new events. Any explanation for this must be based on what makes those common progenitors different from the other pairs. That is, it must involve enough information to pick out by means of their relational properties what makes those that are progenitors distinct from those that are not. So any complete explanation for the elementary causal process B and C together cause A must make use of information that distinguishes B and C from all others. So it cannot be a general and simple law of the kind we usually envision governs elementary events. Candidates for such laws are discussed later. In particular, a definite law that deterministically explains and predicts the causal relations among unique elementary events will not be of the form of the Newtonian paradigm, as each event and each causal link is unique in the history of the universe. They make up a vast set when fully described. Well, it's the totality of the universe, I imagine. There is no general dynamical law that acts on a configuration space of possible states of a small system. One may ask how the approaches to physics, which have an events ontology, deal with this issue. They do it by summing or averaging over an ensemble of all possible histories that connect given in states to given out states. Two examples are Feynman's diagram expansions in quantum field theories and stochastic or quantum approaches to the dynamics of causal sets. This ducks the issue of explaining which events takes place, and also weakens the event ontology. As the elementary events appear only in terms that are averaged or summoned over. But even if we buy this as a necessary expression of the freedom of the quantum world, it is still the case that this methodology departs from the Newtonian paradigm in that there is no continuous evolution on a fixed configuration space. Indeed, nowhere in physics do we have a theory that explains why individual events occur. Most theories within events ontology are quantum theories, such as Feynman's diagram approaches to quantum field theories. According to which every causal history with every possible sets of events and causal relations has an amplitude it contributes to the sum over histories. There are, to my knowledge, no deterministic causal sets models. Instead, those causal set models that have been studied take a stochastic or quantum approach to dynamics. They therefore do not attempt to answer the question of why particular causal sets occur. On the other hand, dynamics fitting the Newtonian paradigm can be derived for coarse-grained descriptions of larger sets of events. So if we are willing to have a coarse-grained rather than exact laws, then we can speak of classes of events. For example, A is the class of events that has two immediate progenitors. These classes require much less information to describe than the individual events. Hence, we can have simple laws applying to large classes of events. These may be quite general, applying as they do to large classes of events. So we see that general and simple laws of the usual kind can emerge from a more detailed description by coarse graining, so that they apply to large classes of events. Relationalism and its limits. Relational versus intrinsic properties. Relationalism is not just a philosophical position. It is a methodological imperative. Progress in physics can often be made by identifying non-dynamical background structures in the description of a subsystem of the universe and replacing it with a real dynamical physical interaction with degrees of freedom outside of that subsystem. The paradigmatic example of this is Einstein's use of what he called Mach's principle, by means of which the role of absolute space in defining the distinction between inertial and accelerated motion in Newton's physics is replaced by the action of the distant stars and galaxies, acting through the dynamical gravitational field of general relativity to influence the selection of local inertial frames. A key step in Einstein's discovery of general relativity was his whole argument, which pointed to the role of active diffeomorphism in wiping out of the background structure of the differential manifold, rendering bare manifold points physically meaningless. The result is that space-time is not identified with metric and other fields on a manifold. It is identified with equivalence classes of such fields under diffeomorphism. As already discussed above, in general relativity, physical events are defined relationally and contingently in terms of physical effects perceptible there. So I end 1297 here, 1298 I think it's here. So Smolin is continue to show fallacies deep within thinking. Things that not sensibly anyone else has even pointed to or intuited. This is absolutely 100% new. And that Newtonian paradigm could not even do reductionism might come as a rather big surprise to anyone who studied the field, even if they'd done it for decades. This is brand new thinking, and it's sharp as a razor blade, but it tends to feel small in the beginning, and then it grows, and then you see it causes everything. Because making it small is one of the things that Newtonian paradigm does. It makes thinking small, it makes experience nonsensical, and other contributions that are very far from positive to us. They're not benign, I would say. Because partly they come from a fault, and on top of that, secondly, they have such an enormous influence today, more than any other single factor on earth. Brown words, and this is how I end today. Thank you very much, and have a very pleasant afternoon. Bye-bye for now. And we end by showing this closed off, air-free nature free, all those things that makes thinking, abstractation possible. I would say this will put everyone into an instinctual mood where all thinking is automatic and deterministic in the way that you don't have any control of it. But there is no determinism out there in the universe.